telescope falling out of the sky right now. Not slowly, not metaphorically. The Neil Gehrels Swift Observatory, a 22-year-old scientific workhorse that has spent 2 decades hunting the most violent explosions in the known universe, is losing altitude every single day. And if nothing stops it, it will re-enter Earth's atmosphere and burn up before the end of 2026. But today, for the first time in history, NASA launched a robot to catch it. This is the story of one of the most audacious space rescue missions ever attempted, a mission built in 9 months, a mission that almost everyone in the industry said couldn't be done, and a mission that, if it succeeds, could permanently change how humanity manages its aging satellites. What is Swift and why does it matter? Swift launched in November 2004 on a planned 2-year mission. 22 years later, it's still working. Its original job was simple in concept but extraordinary in execution. Watch the entire sky for gamma-ray bursts, the most powerful explosions in the universe. These events happen when massive stars collapse and die. In just a few seconds, a gamma-ray burst releases more energy than our sun will emit across its entire 10 billion year lifetime. Swift was built to catch these events. The moment its wide-field gamma-ray detector sees a burst, Swift automatically swivels toward the explosion within seconds, then locks its X-ray and ultraviolet telescopes onto the fading afterglow. No other telescope in history has been able to respond that fast. It then broadcasts the coordinates to every observatory on Earth and in space, acting as a dispatcher sending first responders to a crime scene. In 2 decades of operation, Swift has catalogued thousands of gamma-ray bursts. It helped prove that most long bursts come from massive dying stars, and that the rarer short bursts come from merging neutron stars, a finding that transformed our understanding of how heavy elements like gold and platinum are forged in the universe. In 2022, Swift helped detect what astronomers now call the BOAT, the brightest of all time, the most powerful gamma-ray burst ever recorded in human history, so intense that it briefly disrupted Earth's ionosphere from halfway across the observable universe. Astronomers say there is simply no other telescope that responds the way Swift does. No replacement is in development. Losing it would leave a gap that couldn't be filled for years, possibly over a decade. Why is it falling? When Swift launched in 2004, it settled into an orbit roughly 600 kilometers above Earth. At that altitude, the atmosphere is so thin it barely exists. Swift had no engines to maintain its orbit. It didn't need them. The original plan was that it would stay up there comfortably into the early 2030s before natural decay brought it down. Then the sun intervened. The sun operates on an 11-year magnetic activity cycle. At the peak of that cycle, called solar maximum, it fires off more solar flares, more coronal mass ejections, and more high-energy radiation. That extra energy heats Earth's upper atmosphere, causing it to expand. And as the atmosphere expands, it reaches higher into orbit, creating extra drag on any satellite passing through it. The solar maximum that peaked in 2024 and 2025 was stronger than expected, far stronger. And Swift, with no engines to compensate, started falling faster than mission planners had modeled. By the time NASA ran the updated numbers in 2024, the situation was stark. Swift's orbit had decayed to around 370 kilometers. At the rate it was falling, the telescope would drop below 300 kilometers, the threshold below which a rescue becomes physically impossible, by October 2026. After that, re-entry was a matter of months, possibly weeks. With no replacement mission in development and a science instrument still operating at full capacity, NASA faced a choice that most space agencies have never had to make. Let a perfectly functional telescope burn up, or try something that has never been attempted before. The rescue, building Link in 9 months. In September 2025, NASA skipped its usual lengthy competitive procurement process. It couldn't afford the time, and sent a rapid request to 3 companies already under development contracts for in-orbit servicing technology. Katalyst Space Technologies, a startup based in Arizona, came back with a plan that NASA called technically and programmatically plausible. The task order was worth $30 million, and the timeline was 9 months from contract to launch. In the world of aerospace, where missions routinely take a decade to develop, 9 months is essentially nothing. Katalyst's engineers ordered long lead parts the same day the contract was signed. When suppliers fell behind, they machined components themselves. They compressed test campaigns to the absolute minimum safe duration. At every stage, the deadline dictated how much risk the team was willing to accept, the reverse of how NASA usually operates, where risk tolerance dictates the schedule. What they built is called Link. It weighs about 400 kilograms, roughly the mass of a large motorcycle, and is about the size of a domestic refrigerator. It carries 3 main ion engines, 16 reaction control thrusters, solar arrays for power, and 3 robotic arms, each equipped with LiDAR sensors for precision navigation. Those arms are the critical component. Link has to grab Swift, a telescope that was never designed to be grabbed. Swift has no docking port, no grapple fixture, no dedicated handhold. Katalyst engineers spent months studying pre-launch photographs of Swift to identify where Link could safely seize the spacecraft without crushing an instrument or tearing loose a cable. They built a full-size physical mock-up of Swift, mounted it on an industrial robotic arm, and rehearsed the capture procedure repeatedly. A full-sized engineering model of Link rode on an airtable, essentially a giant air hockey surface, to simulate the frictionless environment of space. One of the engineers' biggest concerns is the insulation blankets covering Swift. After 22 years in orbit, exposed to extreme temperature swings and cosmic radiation, those blankets may have become as brittle as glass. When Link's arms make contact, they could shatter, sending debris everywhere. There is no way to test this in advance. Another risk is the sun itself. The same increased solar activity that set Swift on its downward path is still ongoing. A single large solar storm before Link reaches Swift could accelerate the decay beyond recovery. Swift is currently in a low-power mode it has been maintaining since February, conserving what orbit it has left. The launch today used the last Pegasus XL rocket ever built. Pegasus is an air-launched vehicle. Instead of lifting off from the ground, it is carried to 39,000 feet by a modified commercial airliner, then dropped and ignited. It's one of only a handful of rockets in history capable of reaching the precise orbital plane Swift occupies, on the schedule and budget the mission required. After today's launch, there are no Pegasus XL rockets left. The vehicle is officially retired. What happens next? After reaching orbit, Link will spend several weeks running system checks, testing its engines, deploying its solar arrays, firing each thruster, confirming the robotic arms function correctly. Then it will begin a series of orbital maneuvers to gradually close on Swift over a period of months. When it reaches Swift, Link will run proximity operations, slowly circling the telescope, building up a precise picture of its exact orientation, rotation rate, and position. Then it will move in, extend its arms, and attempt the capture. If the capture succeeds, Link will fire its engines over the following months, gradually raising Swift's orbit back toward its original 600-kilometer altitude. If everything works on schedule, Swift could be back to performing full science by autumn 2026. If it works, it could be in orbit for another 2 decades. The broader implications go well beyond Swift. The Hubble Space Telescope, arguably the most famous scientific instrument ever built, is also slowly losing altitude. Hubble has no engines, and the space shuttle that boosted it multiple times no longer exists. A robotic servicing mission of the kind Link is demonstrating could, in principle, save Hubble too. NASA's Hubble team is reportedly watching today's mission closely. Beyond Hubble, there are hundreds of operational satellites in low Earth orbit losing altitude right now, worth tens of billions of dollars. A proven commercial in-orbit servicing capability would transform the economics of space entirely. Satellites that might otherwise be discarded could be refueled, repaired, and boosted for a fraction of the cost of a replacement. The final question. NASA's own astrophysics director stood in front of reporters earlier this month and said without hesitation, no one thought it was going to be possible. He wasn't being modest, he was being honest. The schedule for this mission is unlike anything NASA has ever attempted. The technology is unproven in this exact configuration. The target was never designed to be serviced, and the window to succeed is closing by the day. But Link is in space now. The physics deadline is set, and for the first time in history, humanity is attempting to robotically rescue a falling telescope before it disappears in a streak of fire above the Pacific. Subscribe All Vault for what happens next.